Low-cost LiDAR-based vehicle detection for self-driving container trucks at Seaport. The self-driving technology has been developed rapidly in the past decades. Due to new sensors, and car manufacturers have become more open. However, fully self-driving vehicles for the public still has a long way to go. Most studies try to focus on self-driving in special scenes, such as park sightseeing car, express logistics vehicle, sweeper, indoor service robot, and special vehicles in the mining area or seaport area. One of the critical issues is that the cost of a self-driving vehicle should strictly be controlled for commercial uses. This paper presents a low-cost LiDAR-based moving obstacle detection and tracking for self-driving container trucks in the low-speed seaport area. We built a CNN model for obstacle detection with a bird's eye view (BEV) map generated from two low-density LiDARs, equipped at the head of a container truck. A boosting tracker is used to achieve real-time processing speed on the embedded module of TX second. Simulation on the collected data shows that our stride dialog model can achieve the highest map on the BEV projection map than other models. The contributions of this paper can be summarized as follows. A low-cost LiDAR-based obstacle detection and tracking system that uses only two low-density LiDAR and GPS RTK is designed. A lightweight CNN model is proposed to fulfill the real-time detection task based on the refined BEV map of LiDAR point cloud. A new dual LiDAR-based point cloud dataset in the Seaport area is also presented based on a novel dataset collected from real Seaport in Ningbo. Background. Different from the research phase, a demo self-driving vehicle can be equipped with the best sensors for different targets. Considering the commercial usage, the cost of the sensor solution is strictly constrained for large-scale deployment of self-driving vehicle. Selection of related equipment and sensors is a big challenge for container trucks, because the traditional camera-based front view cannot offer accurate location information of on-road obstacles. Almost all self-driving systems rely on the LiDAR data. The mainstream solution is to install multiple LiDARs to ensure safety, but at the expense of sensor costs, especially for large trucks. The blind area of a single LiDAR top installation scheme is too large. Related works. LiDAR-based obstacle detection in the self-driving area can be divided into two main categories: LiDAR 3D point cloud detection and LiDAR projection-based detection. The LiDAR 3D point cloud detection model often uses raw LiDAR point cloud or voxelized point cloud as the input to later deep learning models. Due to the huge computation needed for processing the 3D point cloud, reducing the 3D point cloud into 2D projection is a common way. Moreover, this kind of projection can be fused with camera images as multi-model based algorithms. LiDAR 3D point cloud based detection. 3D FCN first changes the traditional 2D convolutional network module into 3D full convolutional network module to process the raw 3D point cloud from LiDAR. The voxelnet first transfers raw point cloud into equally spaced 3D voxels, but the downsampling process also reduces the features of the point cloud. PIXOR can achieve real-time 3D object detection through a proposal-free, single-stage detector that outputs oriented 3D object estimates decoded from pixel-wise neural network predictions. Point grid, a full CNN of classification network, and a UNet segmentation network are presented for different tasks. With raw point cloud input. LiDAR projection-based detection. Complex YOLO presented an oiler region proposal based on BEV projection of 3D LiDAR point cloud. Cristiano proposed bilateral filter-based upsampling to match the front view of point cloud projection with related images. Different filter parameters are analyzed to match the field of view of both sensors, LiDAR and camera. Xiaozhi Chen et al. Also proposed a multi-view 3D object detection network that views different fields of both the LiDAR projection maps and the camera image as input. Our approach. Dual LiDAR perceptive system. As we mentioned above, most of current research works that utilize deep learning model 24 to process 3D point cloud are based on the KITTI dataset. This means that those works can only work with dense LiDAR, such as Velodyne HDL64E. This LiDAR sensor can offer 360 degrees of 64 scan lines of the surrounding environment. However, the price of the sensor is too high. When using low-dense LiDAR, such as Velodyne VLP16, that can only offer 16 laser scan lines, the sampling information may drop to 1/4 of that of the Velodyne HDL64E. Fig 2 shows the perception module of our sensor solution for the self-driving container truck. It can be seen that the two low-density LiDARs are equipped on the corners of the vehicle head. Both of the two LiDAR's laser scan lines can reach the front area and can be combined as a 32 scan line. For the side areas, each LiDAR covers one side. This sensor deployment simulates the attention mechanism of human drivers. Fig 1 shows the difference between our system and KITTI dataset. This means that we can get less stable sensing data for the later process. That is a big challenge for on-road obstacle detection and tracking for self-driving. Although our system has lower sensing performance than dense LiDAR, we investigate several refined modules together to enhance the raw point cloud feature. Fig 3 illustrates the whole workflow of dual LiDAR container truck detection and tracking system. We first calibrate the two LiDAR into the same vehicle body coordinate with the RTK GPS as the origin point. For LiDAR BEV projection, two kinds of maps are generated. The H map only considers the height, z-axis of each point, and the final H map contains only one channel, gray. The HDD map considers the height, z-axis, depth, y-axis, and density values of point cloud as a 3-channel map. EC1 is the calculation of density value at each point of Y, where C is the total points in the local cell. And then, we merge each 3 successive frames, according to the GPS into one, to enhance the point cloud features. As the LiDAR sample frequency is 10 Hz and installed as in Fig 2, 3 overlapped frame for the side view can achieve 48 scan lines, and for front view can achieve 96 scan lines. We also propose a simple voxel height-based algorithm to remove the scan lines on road surfaces. This also leads to clearer obstacle features for later detection. Fig 4 and Table 2 are the detailed CNN architecture of our detector model. Large kernel size of 7 convolutional layer is first used, followed by small kernel of 3 with a stride of 2 that can reduce their original image into half of their original size. Alternate stacking of 3, 3, and 1, 1 convolutional layers with different filters at 317. Layers are used to extract the rich features. At the second last layer, we upsample the map and combine it with layer 8. In this way, we use layers 18 to 23 to extract a 2-layer pyramid feature at 2 different scales for a low layer. All the data used for model training and testing are collected from a seaport area with our self-driving trucks. Totally, there are 3 long sequences collected on both sunny and rainy days. The final dataset contains similar sequences of 4,647 sunny, 4,594 cloudy and small rain, and 3,973 sunny frames, with each having 2 kinds of projection maps based on BEV and well-labeled bounding boxes. Table 3 illustrates the RPS per image, IOU and recall of the 2 models trained and tested on our dataset. It can be seen easily that the models achieve larger IOU and recall when training without data augmentation methods. The recall of your LOV3 Tiny trained on HMAP increases by nearly 10% when shut down the random mode in training phase. Fig 5 illustrates the related projection maps. It can be seen from Fig 5b that simply combining 3 successive frames can increase the features of the obstacle. However, the scan lines on the ground also led to noise. In Fig 5a and Fig 5c, an H-map and an HDD map with elimination of the ground are generated. Without the ground, the vehicle features are clearer and may help improve the later detection. It can be seen easily that the PR curve of stride law can cover all the other curves in Fig 6a and Fig 6c. This means that our stride law performs the best on the 2 kinds of LiDAR projection maps. In Fig 6b, the stride law and the LOV3 Tiny show very similar values at the BEP. The XNER model performs the worst in all the cases, and cannot even converge when dealing with stacked point cloud. In Table 4, the mean average precision map of each model at different intersections over the union, IOU, and LiDAR projection maps is listed. Our model is robust enough for real road conditions. For small IOU 0.35, the stride law only performs slightly worse than your LOV3 Tiny and your LOV3 Tiny 3L when using C3F3G0 and C3F3G1, respectively. Fig 7 shows the PR curves of stride law trained on the 3 stacked projection maps and single frame maps. It can be seen that with more frames, the model can achieve better performance. By eliminating the ground, the models can achieve higher performance. Conclusion. This paper has presented a novel, deep learning-based vehicle detection system with 2 low-cost LiDAR for container trucks in the Seaport area, compared to other commercial solutions presented in Table 1. Our sensor cost for low-speed truck is much more lower. Different kinds of projection maps are trained with a well-designed CNN model. A comparison with state-of-the-art models shows that our model can achieve the best performance on most occasions. Thanks.